So, last class we before we go on to the weighting, how a droplet actually weights and what is the role of contact angle. Last class we said that surface tension actually is a function of temperature and the individual mole fractions of the individual components that are present. So, last class we wrote that. This class let us just finish this. So, this is the variation with respect to temperature, and then consequently these are the different mole fractions of the different species that are present. So, surface tension, how does it vary with constant T. Okay. Now, in this particular case we show that the change in surface tension is actually linked with the temperature and the individual variations with respect to the mole fraction of the individual components that are present in the fluid. Okay. Now, and in here the temperature is in degree Celsius. Okay. Now, how is this useful in any practical applications? Now, let us assume that you have a surface, and this is a very common occurrence at a temperature of Tw. There is a liquid layer that is sitting on the top of this heated surface, okay, and this layer has got a thickness of about delta. Okay. Let us not be bothered about what will be the magnitude of delta. Now, at 2 points on the surface, let us take a point A and a point B. Okay. Now, in this point A and B, what we can see is the temperature at point A is actually more than the temperature at point B. Okay. The temperature at point A is more than the temperature at point B. Okay. So, naturally what will happen is that the surface tension magnitude at point A and point B will be different. Now, since surface tension is normally decreases with increase in temperature, that means if Ta is greater than Tb, then the surface tension at B, okay, will be actually greater than the surface tension at A. So, naturally what will happen is that the flow will be dragged from the area of low surface tension to the area of high surface tension and will lead to a recirculating flow like this. Okay. So, understood. So, because this gradient is negative, it implies the surface tension normally decreases with increase in temperature. So, since B is at a lower temperature than A, therefore, its surface tension value is higher than A. So, naturally the fluid near the interface is pulled towards B from a low surface, from a high surface tension to a low surface tension region, okay, pulled towards the region with higher surface tension. So, the higher surface tension region basically pulls, okay. As a result of that you create this recirculating flow, and this flow is called the Bernard cellular flow. Okay. So, this is called the Bernard cellular flow. This happens when a horizontal pool of liquid is very thin layer of liquid is actually heated from the bottom, okay, and this flow is basically called the Marangoni convection. We will cover more about this Marangoni convection in later when we actually watch it with respect to droplets, but this is basically what is called the Marangoni effect, that is a motion of the liquid is caused due to a gradient in surface tension. Because there is a spatial gradient in surface tension which is created due to a spatial gradient in temperature or a spatial gradient in the individual components, we get a recirculating flow. In this way, in this case it is a recirculating flow and it is called basically the Marangoni convection. Okay. Similar things can happen in other types of mediums as well, in other types of configurations as well, okay. But in general this is what the surface tension driven flow is all about. Okay. Now, let us look at now the weighting and the contact angle behavior coming to the topic, and here also we will find later on that Marangoni flow will be an important aspect. So, weighting and contact angles. Okay. Now, weighting and contact angle, let us assume that there is a surface, whatever that surface may be, okay, and there is a droplet which is basically sitting on that substrate. Okay. Now, this is there is a liquid, this is a liquid medium, this is the gas, this is the solid. Okay. So, the substrate, so the droplet actually sits on this particular substrate. Okay. And as you can see that there is a point, or if this is the side view, from the top view it will be like a circle, right. So, there is a circumference around which, okay, there is a 3-phase contact line. That means there is a liquid, there is a vapor, and there is a solid, okay, all at the same region. Now, this particular substrate, let us look at it. There are 3 surface tensions which are acting on it. Okay. One is called sigma LV, one is called sigma SL, and the other one is called sigma SV. Now, the angle that it makes over here is called theta. So, theta is basically the angle that this droplet makes with this substrate. Okay. We will talk about these things a little later. Okay. So, in addition to the surface tension, at LV interface, okay, there are surface tensions that exists. Surface tension exists, okay, between SL and SV interface as well. Okay. Now, the contact angle theta, okay, is the angle between the tangents of SL and LV interfaces. Okay. So, there is an LV interface, okay, and there is an SL interface. So, the angle, so if you draw the tangent, of course, with a solid surface the tangent is nothing but the horizontal line. The LV interface, it is at that particular point, if you look at that particular point, it is the tangent that it makes. Okay. If you draw a tangent to the liquid surface, that is basically the angle. So, this is the contact angle, is the angle between the tangents of the SL and the LV interfaces. Okay. So, the contact line is basically, contact line is the locus of points, basically locus of points where the 3 phases intersect. That means, as you can see, that if you highlight this particular point, this is the point, or this is the circumferential region, okay, because what you look as a point in the side view, it is basically as the circumferential or perimeter type of a line. This is nothing but the contact line. Okay. So, the contact line is basically that. Okay. So, the contact line is defined only for equilibrium positions. Contact line, the contact angle is defined for equilibrium condition. Okay. So, the equilibrium condition means that the droplet is at a static condition, it is not moving, okay, and that relationship is given by cos theta, where theta is the angle made by the tangents, this and this, okay, sigma SV minus sigma SL divided by sigma LV. Okay. So, this is basically called the Young's equation. Okay. So, it is basically nothing but a force balance in the horizontal direction. So, if you look at this particular expression, Okay, what does it actually tell you when it is an equilibrium condition? Okay, so this is basically sigma SV, okay, sigma SV, okay, and then is sigma SL. So this points towards the two directions, the positive and the negative axis. This is basically decomposed in this direction, so that this will be nothing but sigma LV cos theta, okay, and then if you do the math, this has to be equal to this because all of them are acting on the perimeter. Okay. So, all of that thing cancels out, okay, and therefore, you get this particular relationship from the Young's equation. Okay. So, let us look at this thing in a little bit more details. It is basically nothing but a force balance. So, Young's equation is nothing but a force balance which gives a relationship between the contact angle, which is theta, and the corresponding surface tension values between the solid vapor, solid liquid and the liquid vapor interfaces. Okay. Now, let us look at this thing in a little bit more details. Okay. Now, this is valid only when it is in a equilibrium condition. Now, let us look at when there is a relative motion. When there is a relative motion of the liquid drop over a solid surface, when there is a relative motion of the liquid drop over the solid surface, a different contact angle can be expected. Okay. When the relative motion stops, so when there is a relative motion of the liquid drop, that means there is, as you know, the surface is there. Now, as you deploy the droplet, it actually spreads or it actually contracts, right, whatever may be the situation. So, there is a relative motion of the drop over this solid surface. Okay. At that point of time, a different contact angle is expected almost at every time instant, right, when it is actually spreading or it is actually contracting. When the relative motion actually stops, okay, so after this at some point it will assume, say, a shape like this. So, this is the point where the relative motion has actually stopped. Here it will show an apparent contact angle or a contact angle rather, let us not put it as apparent, contact angle which is different from the apparent or equilibrium contact angle. Okay. So, when there is a relative motion between the two surfaces, when the relative motion between the drop and the surfaces, there is a contact angle is different at each time instant, and when this relative motion stops, this contact angle is different from the equilibrium contact angle that we defined earlier. Okay. So, it also depends, this contact angle also depends on the direction of motion. The direction of motion of the droplet, that means whether it is spreading or whether it is contracting, the direction of the previous motion. This angle depends on the direction of the previous motion, that means whether it is advancing or receding. Okay. Now, let us look at the presentation so that we can get an idea that we have. Okay. Okay. Now, this is, for example, a pictorial diagram in which we show that this is the apparent contact angle. So, you can see that this is what the droplet actually makes. Okay. This is for a stationary liquid, the first one. Okay. So, that is the apparent contact angle that you make. Let us not be bothered about those kinks that you see. Okay. This is the apparent contact angle that it actually makes. Now, in some cases, say for example, if the liquid flows upwards, okay, then you get what we call an advancing contact angle, okay. And in the other case when the liquid flows downwards, okay, downwards and this is upwards, okay, you get a receding contact angle. So, that means here the droplet is kind of its contact angle is actually decreasing or increasing rather. In the case of receding, it is actually getting more and more like a flattened pancake type of a form. Okay. So, this is what the liquid flows downwards, this is what happens when the liquid flows upwards, this is the advancing contact angle, this is the receding contact angle. Okay. Now, that is important because this is the direction of motion, this is the static and stationary shape. These are the two possible motions that you can get. So, you can get both advancing as well as both receding contact angle. Okay. And we will show some of the cases, say for example, this table 5.1 if you look at it, okay. Say the two substrate is aluminum, the liquid is acetone. Okay. So, here you can see the upper and the lower values, okay. That is 25 is the upper value, 11 is the lower value in the degree for advancing and the receding. So, advancing liquid will advancing acetone drop will exhibit a contact angle of about 25 degrees Celsius and the receding drop will exhibit a contact angle of about 11. Okay. In the case of water, this difference is this is beryllium with acetone. In the case of aluminum with water, you can see that there is quite a bit of a difference in the advancing and the receding contact angles. Similarly, there are values given for acetone nickel combination. Okay. These are the two, these are very low values of the contact angle, that means it would translate to a very thin liquid layer, okay, or a liquid cap like this. Okay. For water, however, when you actually have a situation like this is more bulgy, but it is still not 90 degrees, it is below 90 degrees. Okay. So, that is why it is like this. Okay. So, similarly here we can see for ethanol, of course, because of the lower surface tension, all these values are a bit lower on the lower side. Okay. So, ethanol and water, because of the high surface tension values, exhibits a higher contact angle. Acetone is also not very high surface tension. So, all these things actually shows the two ranges of values. Advancing will be obviously higher because the liquid is actually contracting like this, okay, and receding will be obviously lower, okay, because the liquid is actually spreading. So, the previous motion is actually spreading. Okay. So, these are the two types of motions that you will normally expect to see in these cases. Okay. Now, however, for rough surfaces, if the surface is rough, okay, for rough surfaces, the contact angle that is exhibited by the rough surface is given by basically gamma cos theta. Now, gamma cos theta, where gamma is basically the ratio of rough surface area to smooth surface area. Got it. So, if you have a surface which is given like this is a smooth surface, right. Now, if you take another surface of similar kind, but you have all these roughnesses which are ingrained on the top, right. Okay. So, your contact angle in this case versus the contact angle in this case will be different. Okay. In fact, the contact angle for this particular case will be a function of gamma into cos theta. So, cos theta is the contact angle for this. So, this is your cos theta. Okay, this gamma cos theta, gamma is a ratio of the rough surface area to the smooth surface area. So, obviously one can see that gamma will be greater than 1, right, for rough surfaces. It has to be, by definition the gamma will be more than 1. So, naturally the cos theta rough, okay, will be greater than your cos theta. Okay. So, cos theta rough will be greater than cos theta, which would imply that the rough surface, the cos component of the contact angle is always more than what you expect on a smooth surface, right. So, this is one of the key relations. So, of course, the substrates are still the same, you cannot compare the roughness across two different substrates, it is the same substrate. Say for example, you take aluminum and you have a very smooth finish where the RMS roughness is very, very low. On the other hand, you have another substrate in which the roughness values are very high. So, therefore, there is a lot of as I showed roughness is like this, right, okay, and in the other case the roughness is like that. So, naturally this is more rough than this, and when you place a droplet on this, obviously the contact angle on this will be different than the contact angle over here. So, moving on, let us look at the journal entry. Okay. So, now we know that what the contact angles are. Now, let us, we are in a perfect situation now to define something called weightability. Now that you know what an advancing and the receding contact angles are. Okay. So, when we define weightability, non-weighting, we define categories. Non-weighting surfaces are where the contact angle is falls in this range. That means, the contact angle is greater than 90 degree, but less than 180 degrees. I can draw, this will be more or less like this, and it can go up to like this. So, it is called hydrophobic surfaces essentially. So, for example, if you put wax on a surface and you put a droplet on the top of that, you will find that it almost sits like a sphere, almost completely like a sphere. That means, the contact angle is very high, close to 180 degrees. Okay. Partially weighting contact angle will be 0 greater than theta less than 90 degrees. Okay. So, that means, this particular thing exhibits anywhere between this to this, okay. And completely weighting would imply theta is equal to 0 degrees. That means, it is a film, flat film. Okay. So, this is more like hydrophobic. We will check what hydrophobic are. Hydrophobic, this is more like hydrophilic, and this is completely weighting. This is a thin film, completely weighting thin film, and thin film we will do in a lot of details later on. Okay. So, this actually gives you the first idea, the definition of weighting. Okay. Now, if you imagine bringing a small amount of liquid with an initially dry solid surface, okay, liquid, there are several possibilities. The liquid may not weight the surface, it might actually form these droplets, and these droplets actually sits on the substrate. On the other case, the liquid may actually completely weight the surface and form a film. So, there are two possibilities that can actually happen. Okay. So, what is weightability dependent on? Like in some cases it spreads, in some cases it forms these nice spheres. Okay. So, what determines? So, you have a substrate and in which you try to deploy a liquid. Okay. So, you bring basically a pipette or a syringe like this, okay, and it can form something like this, it can form something like that, it can form something like this, or it might actually completely wet the surface. So, what determines this to this and this to this? Okay. So, weightability is attributed to the strong intermolecular force near the sub interface between the solid and the liquid. So, it is basically nothing but the strong intermolecular forces between the solid and liquid, right, between the solid and the liquid, forces between the solid and the liquid at the interface. Okay. So, that is the most important criteria. We will cover it a little bit more details later, but it is basically the nature of interaction between the substrate and the liquid. So, it is dependent on both the substrate as well as the liquid. So, they are like pairs, okay, and that is what determines that whether a droplet will sit nicely or it will spread. So, it is highly dependent on the surface properties, and as a result of that the intermolecular interactions between the solid and the liquid at the interface. Okay. So, we will stop at this particular lecture over here. In the next lecture, we will speak on the spreading and the disjoining pressure. Okay. Thanks.